We know that drift velocity is equal to mobility into electric field. But will the drift velocity keep on increasing with the increase in electric field infinitely? If that was the case, we would have proved a very famous statement wrong, which was actually given by Einstein. That was, no particle having mass at rest can move with speed greater than the velocity of light. But unfortunately, drift velocity has its limit, thereby limiting the drift current also. To understand the concept, we will draw a plot of mobility versus electric field, and correspondingly we will draw a plot for drift velocity with electric field. We will divide the graph into three regions: R1, R2 and R3. For region R1, initially when the intensity of electric field is comparatively small, then the mobility is independent of electric field, and a rough value of electric field up to where mobility remains independent of electric field is 1 kilovolt per centimeter. However, this value will change for different semiconductors. So we will draw a straight line in the region R1 for mobility versus electric field graph like this. And if we talk about drift velocity, which is proportional to electric field, then we will get a straight line with a non-zero slope for the graph of drift velocity with electric field. Now, for the region R2, when we increase the intensity of electric field further, resulting in the increase of kinetic energy, the interactions between electrons and the lattice also increases, thereby reducing its mobility. So, in the region R2, mobility is inversely proportional to electric field intensity raised to the power 1 by 2. So, we will get a parabolic graph for the region R2. And if we talk about drift velocity, then we know that it is directly proportional to mobility, and also it is directly proportional to electric field intensity. But since mobility itself is dependent upon electric field intensity raised to the power minus 1 by 2, we can write drift velocity is proportional to electric field intensity raised to the power 1 by 2. This will also give a parabolic graph. So for the region R2, we will get the graph for drift velocity versus electric field like this. Now for region R3, the electric field intensity is so high that mobility of the semiconductor is inversely proportional to electric field intensity. Curve for the graph of mobility versus electric field intensity to be like this. Similarly, we know that drift velocity is dependent upon mobility as well as electric field intensity. But since mobility is decreasing such that it is inversely proportional to electric field intensity, therefore drift velocity will become a constant, and this constant is also called as saturated drift velocity. So the graph will come out to be a straight line. You should remember that we have taken only rough values of electric field intensity of 10 to the power 3 and 10 to the power 4, but these values will change for different semiconductors, as well as this value will change for different carriers, meaning that the curve of drift velocity as well as mobility will be different for electrons and holes for the same semiconductor. Now, if we take silicon for reference, saturated drift velocity is of the order of 10 to the power 7 centimeter per second. The value for saturated drift velocity changes for electron and holes, however, they change only slightly. In the region R3, where the electric field is so high, the number of interactions between electrons and lattice increases significantly. These interactions or collisions results in the dissipation of heat energy due to the emission of phonons. Obviously, this is an unwanted phenomena as the electric energy is dissipated as heat rather than increasing the kinetic energy of electron, which would further increase the drift velocity and also the drift current. Another point that you should remember that the saturated drift velocity is dependent upon temperature. So, at different temperatures, saturated drift velocity will come out to be different for the same semiconductor. And the value of saturated drift velocity of 10 raised to the power 7 centimeter per second was determined experimentally at 300 Kelvin. Now we will see some formulas which were found out experimentally and can give you approximate value of drift velocity. Drift velocity for electrons is given by similarly drift velocity for holes is given by VD set is saturated drift velocity, and at 300 Kelvin the saturated drift velocity is of the order of 10 to the power 7 centimeter per second. Here EON and EOP are the values of electric field where the electrons and holes for the silicon semiconductor can be assumed to have achieved the state of saturation, and the value of EON, which was found experimentally, is approximately equal to 7 into 10 raised to the power 3 volt per centimeter. Similarly, the value of EOP is equal to 2 into 10 raised to the power 4 volt per centimeter. These values of EON and EOP are not universal. These values are valid only for silicon semiconductor. For a small value of electric fields, the drift velocity is reduced to by seeing the formulas at low electric fields, we can see that the drift velocities are linear functions of the electric field. Most of the semiconductors have similar graphs for drift velocity versus electric field. However, for few semiconductors like gallium arsenide, the curve for drift velocity versus electric field for electrons comes out slightly different, which is like this. So, the drift velocity first linearly increases with the electric field, and there will be a portion in which the drift velocity is actually decreasing when we increase the electric field, and this particular region is said to have negative differential mobility. You know that mobility is actually equal to drift velocity divided by electric field. Similarly, differential mobility is nothing but the differential of drift velocity with respect to electric field intensity, or you can say it is the slope of the curve at any point. This region in the graph of drift velocity versus electric field, in which we get negative differential mobility, occurs because of presence of different values in EK diagram of the semiconductor. For example, initially all electrons are present in the lowest valley of the conduction band, and when the intensity of electric field is also low, then the mobility of electrons increases linearly with electric field. And you also know that the effective mass of charge carriers is dependent upon the energy band level. So here The electrons have effective mass m1, where m1 is effective mass of electron, which is equal to approximately 0.067 m0. Usually effective mass is denoted in terms of m0, where m0 is the rest mass of an electron. But when we increase the electric field intensity, the electrons absorbs sufficient energy to move to higher energy values of conduction band. And in the higher valley, the mass of free electrons is m2, where m2 is the effective mass of free electron at the higher energy level valley, which is equal to around 0.55 m0. You can observe that effective mass of free electron increases, which ultimately reduces its mobility. Thus, the mobility will keep on decreasing unless all electrons come to higher energy level valley, and afterwards it gets saturated. This is quite a special phenomena which is present in gallium arsenide, and remember that this phenomena is present only for free electrons. This does not happen for holes in gallium arsenide. This property of gallium arsenide of having negative differential mobility is used while designing oscillators.